En dit wordt verkrijgen van de graad van dokter in de ingenieurswetenschappen. Ik zal het proefschrift nu verdedigen. Ondertussen vraag u om uw werk voor te stellen in ongeveer 3 kwartier. Ja. Nadien hebben we tijd voor discussie met de leden van de examen.
Prima.
De floor is yours.
Dank u, meneer de voorzitter. Thank you for coming. I think by now, most of you already know that ventilating indoor spaces is very important because of the whole COVID pandemic. It was all over the news that we had to ventilate our indoor spaces. And this is because ventilation controls the indoor air. So for example, in this auditorium, the indoor air can contain many contaminants, such as, for example, the CO2 we all exhale, or materials that can emit pollutants as well. Potentially, there are some bacteria, viruses present in the indoor air, so therefore we need to add fresh ventilation air, and the room air should be extracted to minimize these contaminant concentration levels as much as possible. Another task of ventilation is that it controls the thermal environment, so in order to have a comfortable indoor temperature, ventilation is needed. A downside is that often energy consuming equipment is needed to supply this fresh ventilation air. Especially in airplane cabins, ventilation is very important because it's an airtight envelope. When in flight, it's surrounded by harsh outdoor conditions, so very low temperatures, low atmospheric pressures. And inside the cabin, a lot of passengers are present. So they all exhale CO2, for example, so there is a large production of contaminants, there is a large heat load, so therefore ventilation is really necessary. To give an example, without ventilation, the comfort level of CO2 would be exceeded within minutes. And there is a case of a disease transmission. It was in 1978, in which the airplane was on ground for several hours, and the ventilation system was not turned on. And just because there was one ill passenger, 72% of the other passengers were infected as well. Another task of ventilation is to pressurize the cabin, because without ventilation, we weren't able to breathe in an airplane. The environmental control system, or the ECS, controls the supply air, which is the largest power consumer of the non-propulsive systems. And let's have a look how the ECS provides the ventilation air to the airplane cabin. I will be very brief here, so I will only explain very shortly the main working principle and only show a couple of subsystems of the ECS. So first there is the pneumatic system, which extracts the ventilation air. It's actually coming from the engines of the airplane cabin. There the air is already compressed. It's still at a high temperature, so eventually it will reach the air conditioning system, where air is cooled down to the temperature that is desired. And then through a lot of subsystems, it will eventually reach the air distribution system. So then air is supplied, fresh ventilation air is supplied to the cabin. The main ventilation method used in airplane cabins is called mixing ventilation. And in mixing ventilation, fresh air is supplied above the passengers at a relatively high momentum in order to mix sufficiently with the cabin air. And as you can see, large recirculation cells are formed, which basically distribute the air throughout the cabin. An opposing jet configuration, as shown over here, with, for example, 2 ceiling jets or 2 lateral jets, is very often used for such a single aisle airplane cabin, and the cabin air is extracted at floor level. There exist some drawbacks for this mixing ventilation method, which basically drives research on alternative methods. For example, displacement ventilation, as you see at the lower image. In displacement ventilation, air is supplied at a lower momentum below the seats, and it will eventually heat up, and it will displace the air towards the outlets that are located on the top. So it displaces the air, it doesn't mix. So the mixing basically provides or gives a lower ventilation performance compared to, for example, displacement ventilation. And the ventilation performance can be expressed using these measures. So for example, on the left-hand side here, the air change efficiency. which basically measures the actual time needed to replace all the indoor air compared to the theoretical shortest possible time to replace all the indoor air. So it's a measure of how efficient the fresh supply air reaches every point in the cabin. The contaminant removal effectiveness in the middle is concerned with the dilution of contaminants and the extraction of contaminants, and heat removal effectiveness on the right-hand side is the same as contaminant removal effectiveness, but concerns the heat instead of contaminants. Some numbers I found in the literature for the air change efficiency and heat removal effectiveness. You can see that for mixing ventilation, these the values are more or less or almost always lower than for displacement ventilation. For the contaminant removal effectiveness, I wasn't able to find any numbers in the literature. Other drawbacks are, for example, stagnant zones that can be present. For example, in the center of the large recirculation cells over here. In stagnant zones, contaminants can build up, so this is undesired. Short circuiting could also occur, which means that the fresh supplier is directly going to the outlet flow, so it's extracted from the cabin without sufficiently mixing first with cabin air. Such a mixing ventilation flow could also show some unstable flow behavior, which is also undesired. So ideally, you would like to control the flow field as much as possible. However, such alternative ventilation methods as displacement ventilation, they also have their deficiencies. So for example, they experience difficulties with implementation related to high costs, interior design restrictions. And with deficiencies, I mean, for example, displacement ventilation, it cannot be used for heating the cabin, or it performs very bad for heating. So since mixing ventilation is still the most used airplane ventilation method, and airplane manufacturers still tend to use this method because of its robust design, its easy implementation, the question of how to improve this mixing ventilation performance is still very relevant. The mixing ventilation performance basically depends on the induced ventilation flow patterns and the underlying flow components, which are driven by the supply jets. So with fundamental flow components, I mean the supply jets, their interaction into a merge jet, these recirculation cells over here, but also thermal buoyancy. So the thermal buoyancy plumes raising above the passengers. I would like to mention here that thermal buoyancy effects are considered to be of secondary importance given the primary influence of the supply jets, which really mainly drive the flow field. So therefore, in my thesis, I only focus on isothermal conditions. I did not consider thermal effects. So we would like to improve the mixing ventilation performance, and therefore there is a need to obtain a detailed investigation of all these flow patterns and the underlying flow components. And of course, we need to think about novel mixing ventilation concepts that may improve its performance. However, current literature fails to address these needs. So the fundamental flow components are only scarcely investigated in current literature. There exist some airplane cabin studies, for example, the one shown over here. These researchers, they used a cabin mock-up, it's a laboratory setup, and they indeed investigated the airflow patterns as indicated over there, like the lateral supply jets, their interaction, the recirculation cell. However, since they used a realistic mock-up, it has a lot of details. These results could be case specific. So there might be a need to construct a more simplified model, such as the Aachen model shown over here, where you have two opposing wall jets at the top. These researchers, they did not look in more detail they didn't investigate in detail the underlying flow patterns. They mainly gave a description of the overall velocity field, temperature field, without going into detail on the fundamental flow component characteristics. Such a detailed characterization has been performed in such even more fundamental studies. However, these studies use an open environment, while an airplane cabin is definitely an enclosed environment, so you have these return flows that can have a very large impact. So basically, this defines my first objective. We designed a generic experimental setup consisting of a simplified cabin model in order to study such opposing jet configurations, but also the underlying flow components. The literature also mainly describes the mean flow behavior. The instantaneous flow behavior is rarely described. So this defines my second objective of the thesis. I analyzed both the mean and the instantaneous flow behavior of such an opposing jet flow. Mainly steady simulations, so time-independent simulations have been used in the literature. Therefore, I performed steady but also transient CFD simulations. And novel mixing ventilation concepts are missing because researchers tend to investigate alternative ventilation methods. So this is why I investigated time periodic ventilation, as I will explain later, as a novel mixing ventilation concept. The three parts of the thesis consider each of these objectives. Here you see an overview of the thesis. So I performed a systematic investigation, both consisting of measurements and CFD simulations. Let's focus on part one. First, I will show you how we designed the setup, the experimental setup. As mentioned, it's a simplified setup. It's shown at the right-hand side. It has a generic geometry. It's at reduced scale, so reduced length scales. Its width is 30 centimeters, the height is 20 centimeters, but the width to height ratio is the same as used in airplane cabins. It's water-filled because it's reduced scale. As you probably also noticed, it's an empty enclosure, so no seats are incorporated, no passengers are incorporated, so it's isothermal as mentioned. Here you see some images. The middle image shows a close-up of the conditioning section at the inlet. At the right-hand side, you see the valves that are connected to each of the individual inlets. So by controlling each valve, we can regulate the inlet velocity, and the inlet velocity was chosen such that the Reynolds number, which basically represents the inlet velocity, was in a transitional regime, the same as used in airplane cabins. I investigated two opposing jet configurations, so a ceiling jet configuration with the ceiling inlets open, and a lateral jet configuration with only the lateral inlets open. Particle image velocimetry, or PIV measurements, have been applied, and important to mention here is that the laser light basically illuminates the vertical midplane. This was the measurement plane. So I measured the flow field in the vertical midplane of this setup. The measurements, each measurement was taken for 15 minutes at a sampling frequency of 15 Hertz. So I collected 13,500 instantaneous snapshots of the flow field. In total, I performed 6 measurements, 3 in each opposing jet configuration. And I would like to mention here that although I tried to carefully match the inlet conditions of the opposing jets, there's still a slight deviation in, for example, the Reynolds number or in the turbulence intensities. This is you should keep this in mind for a moment. Now let's show the results in both configurations. First, the configuration with opposing ceiling jets. And I will show the instantaneous flow field followed by the mean flow. So this is how the flow field looks like. You can clearly see both ceiling jets coming from the ceiling inlets. They interact here around the vertical center line of the enclosure, which shows transient interaction zone shifting from left to right across this vertical center line. And this interaction zone drives the merge jet, which appears to flap from left to right. Some specific observations for one specific measurement, one of the 3 measurements, are that this measurement, as opposed to the other 2 measurements, showed some stronger deviations of the merge jet location from the vertical center line. And this is what is shown in this figure. So on the vertical axis, you see the location of the merge jet as a function of the time. And the green curve, which belongs to the measurement I'm talking about, the green curve shows some deviating flow, shows some deviating positions, meaning that the merge jet is really located for 20 up to 60 seconds closer to one of the 2 inlets. At such instances, the flow field can even become unstable, as you can see here. This clearly shows some unstable behavior, which could be due to the fact that in this measurement, the inlet conditions were a bit more balanced. Compared to the other measurements, there was a larger difference in supply velocities, for example, which could mean that one of these jets is suppressing the opposing jet more, which gave a more stable configuration. Also, 3D effects could be present, but this I didn't test because I performed 2D PIV measurements in one plane only. As already stated in the literature, one should avoid air conditioning of an aircraft cabin using settings for which the flow field is not stable. Then by inspection of the flow field, I observed a lot of vortices, so I tried to visualize them, I tried to track them over time. What is important to mention here is that such vortices, or in Dutch it's called wervels, such vortices, they can be affected along with the flow, along the merged jet, and you can clearly see that high momentum fluid from within the core of the merged jet is transported to the sides. So such vortices really contribute to the mixing of in the enclosure. Then let's take a look at the mean flow. How does it look like? So first I will show you the overall flow field. The flow patterns look like this. So the mean flow is obtained by averaging out all the individual PIV samples. You can clearly see that two large recirculation cells are formed. Then I inspected vertical profiles, horizontal profiles. I will just briefly show them. The vertical profiles, horizontal profiles of the velocity components, also of the Reynolds normal stresses, Reynolds shear stresses. So these Reynolds stresses, they basically represent the velocity fluctuations or which are related to turbulence levels, if you want. We analyzed the horizontal profiles as mentioned, so we could clearly see from this image, which represents the vertical velocity over the height, it clearly shows the development of the merged jet, which also becomes wider because of the mixing at its sides due to these vortices I've shown. In the interaction zone, high turbulence levels are present, indicating that this is really like a transient, it's really shifting back and forth along the center line. Also, high turbulence levels are present along the sides of the merged jet. Besides the overall flow field, I also investigated the individual flow components. So for each flow component, I derived several characteristics. What I would like to show here is that indeed in mixing ventilation, stagnation zones can be present. And in case contaminants would be present inside my experimental setup, they might build up in such areas, which is of course unwanted. Let's have a brief look on the lateral inlet configuration. I will only show you give a brief outline of the results over here. I showed the results of the sealing inlets in more detail because I will use these measurement results in part 2 later. So the instantaneous flow looks like this. We can see a deflecting oscillations with a specific frequency, which is also similar as in airplane cabins. Besides the deflecting oscillations, some horizontal oscillations with higher frequency were observed. This is basically the situation in between these deflecting oscillations when both jets really try to displace each other. Vortical structures were again investigated. Then some results of the mean flow. So again, I've observed or I investigated the overall flow field in terms of the flow patterns. Vertical, horizontal profiles were observed. And again, a characterization of each of these flow components was made. So part 1, in short, I developed a new experimental setup that consists of a simplified cabin mockup. And this cabin mockup really shows flow patterns or phenomena similar to opposing jet mixing ventilation. It showed indeed some stagnant zones and flow instabilities, but also vortices that can contribute to the mixing. The measurement data can also be used as a benchmark for the CFD simulations, which basically means that if we perform CFD simulations, we can use the measurement data for comparison to assess whether the CFD simulations are accurate. More information can be found in the papers mentioned over here. This brings me to the second part of my thesis, in which I performed CFD simulations in this simplified cabin, and I tried to assess the accuracy of several CFD methods using the measurement presented in part 1. So first we construct a computational domain as shown over here. Then we constructed computational grids. I constructed two computational grids with a different resolution, a basic grid and a finer grid. The grids are wall resolving. The boundary conditions are taken equal as in the experiment. However, I should mention that because in the experiment the inlet conditions differed a bit between the two jets, I took the average value, and the average value has been used for the inlet conditions of both jets in the simulations. We choose the correct computational settings, then the turbulence modeling. So I tested two different turbulence models, GANS and LES, which I will show you on the next slide what it means. Therefore, I use this drawing of Leonardo da Vinci, in which you can see a water stream flowing into a pool. And it's creating a turbulent flow consisting of many different vortices, ranging from larger scale vortices all the way down to smaller scale vortices. In the GANS, none of these vortices, or none of their energy, like the turbulent kinetic energy as we call it, none of the turbulent kinetic energy is actually resolved. Only the mean flow is resolved, and all the turbulent kinetic energy is modeled. While in LES, which is also called the scale resolving method, a large part of the turbulent kinetic energy spectrum is resolved, and only the smaller scale eddies are modeled. To give you an idea about how such a flow field looks like, in GANS you can see that this is the mean flow behavior. In LES, this is an instantaneous, this is an instant of an LES simulation. So LES is a time-dependent, it provides a time-dependent flow field. You can also clearly see that there are more details inside the cabin. So in order to compare the LES simulations with GANS, we need to time average the results. The modeling part is controlled by either turbulence models in GANS or by subgrid scale models in LES. And I tested 3 different GANS models and 2 LES models. So the GANS models, I tested 2 K epsilon models, the RNG and the low Reynolds number model, and 1 K omega model, the SST K omega model. The LES subgrid scale models are the whale and the dynamic kinetic energy model. So I performed 5 simulations in total. The first thing we need to do is to verify the solution, which basically means that we verify whether the grid resolution is sufficient. Can we use the basic grid resolution, or should we use the finer grid resolution? From these analyses, I could conclude that the basic grid resolution was sufficient, so we can use the results of the basic grid obtained on the basic grid to validate the solution, which means that we will now validate which method, which simulation shows the most accurate flow predictions comparable to the measured flow. So comparison of the overall flow field. On the left-hand side, you see the measured flow field. On the right-hand side, the simulations, with on top the 3 GANS simulations, at the bottom the 2 LES simulations. And we could already see that the overall flow patterns, they are represented in all simulations. But there appear some specific differences. For example, the K epsilon models, they show some higher velocities in the core of the merge jet. And the SST K omega model shows the size of the interaction zone, which is also larger compared to the measurement, which is less accurate. Then by comparing the vertical profiles and applying validation metrics, so with validation metrics are basically some mathematical formula that give you a quantitative that gives you a number which shows how good the agreement is between measurements and simulations. And we could conclude that both GANS simulations actually show very similar performance. The velocity predictions are reasonable, but the Reynolds stress predictions or the turbulence levels, they are poorly represented. The SST K omega model shows to be better, which is basically because this model showed oscillatory convergence. So with the K epsilon models, a steady flow solution was obtained, whereas with the SSTK omega model, you could clearly see that it was alternating between steady state solutions, which are basically the flow states of the underlying transient opposing jet flow. Same analysis we did for LES. We could see that both subgrid scale models, they show similar velocity predictions, but they show a much better Reynolds stress predictions compared to RANS. So in general, LES performed better than RANS for the overall flow field. Let's have a look at these flow components. With in light blue, the observations derived from the simulations. In conclusion, again, LES for most of these flow components performed better than RANS. So part two, in short, the RANS K epsilon models, they are incapable of correctly capturing the mean behavior of the highly unsteady opposing jet flow. As the SST K omega model, because of the oscillatory convergence, it covered part of the unsteadiness, where, however, LES is needed for the accurate representation of opposing jet flows because of its unsteady and scale resolving properties. However, it should be mentioned that LES also requires much higher simulation times, even up to a factor of 41 compared to RANS. So this is important to consider. More information can be found in the publication cited over here. And this brings me to part three, the last part of the thesis, in which I performed CFD simulations in a realistic airplane cabin. Because of the principle of subconfiguration, which I used the information of part two, which showed that LES showed the best performance. Therefore, I can use LES simulations in a real airplane cabin as well. And I will evaluate the concept of time periodic ventilation. Again, first the computational domain is constructed. So it's a model of a single aisle cabin model, similar as an Airbus A320, as shown on the right hand side. I also constructed a realistic model of the passengers. All resolving grids are again constructed. The solution was verified, so the grid resolution you see in these images was sufficient. Computational settings are chosen, and for the turbulence modeling, LES is used, based on the results of part two. Some boundary conditions. So contaminants are produced inside the cabin via all the passengers. So all the passengers are actually breathing out. It's modeled as a constant flow rate and as a passive gas. And at the inlet, I evaluated statistically steady supply velocities, and I will compare it to time periodic supply velocities. So statistically steady ventilation basically means that the supply velocity is constant over time. This is how current ventilation works. And we try to investigate what happens if we would add a sinusoidal contribution to the inlet velocity. So what happens if the inlet velocity is varied over time according to a sine function? With a specific period approximately equal to 10 seconds. So it's a relatively rapid variation. And the amplitude of the sine signal was taken maximum in my study. So what is the effect of time periodic ventilation on the opposing jet cabin mixing ventilation efficiency? And note that on purpose, I used the word mixing ventilation efficiency. In the beginning, I was talking about mixing ventilation performance, for which we could use these three parameters. Now with mixing ventilation efficiency only considers the first two parameters because I performed isothermal simulations and I could not obtain any results. I could not find the heat removal effectiveness because no thermal effects were present. This is how it looks. So here we see the velocity distribution and the vertical cross section. This plane is actually crossing the legs of the passengers. And you can see in the steady ventilation case that 4 inlets are used and they all interact along the middle, so creating the merge jet. For the time periodic ventilation, I tested 2 different time periodic ventilation strategies. One, which I call an asymmetric supply, in which you can clearly see an asymmetric shifting of the flow field from left to right. So the left inlets are synchronized and the right inlets are synchronized. While in the symmetric supply case, you can see that the top inlets are synchronized and the lateral inlets are synchronized. Important to mention is that in the time periodic ventilation cases, the total amount of supply air remained unchanged compared to the steady ventilation case. Now let's have a look at the results. So time periodic ventilation appears to improve the fresh air distribution. So this is in the steady ventilation case. The air is distributed according to the arrows indicated over here. With the asymmetric supply, you can clearly see that air is delivered more efficiently to the passenger zone. Larger scale vortices are also generated below the lateral inlets. So each time the lateral inlet increases, a large vortex is formed, which also contributes to the spread of fresh air towards the passenger zone. For the symmetric supply, we get a more pulsating flow behavior. So each time the lateral jets increase in velocity, we can see that large amount of fresh air reaches the passenger zone. From this, we can calculate the air change efficiency, which improves in case of the time of the asymmetric supply. But for the symmetric supply, it actually doesn't improve at all. It becomes worse. This is because when we look at the full volume, in case the top inlets, they reduce in velocity, some contaminants can build up in the upper part of the enclosure. If we look at the passenger zone only, we can see that both time periodic ventilation cases show an improved performance compared to steady ventilation. Then the effect on the mean contaminant concentration. So here you see the mean contaminant concentration of exhaled air in two planes, a vertical cross-section and a horizontal section at the bottom. The horizontal section basically crosses the heads of the passengers. And you can see that the contaminant concentration levels are lower under time periodic ventilation compared to steady ventilation. Note the stagnant recirculation cell center that appears under steady ventilation, where contaminants can indeed build up. If you look at the separate zones, we can see that in the passenger zone, the contaminants decrease, but in the surrounding zones and at the outlet, contaminant concentrations increase, which basically means that contaminants are transported from the passenger zone towards the surrounding areas. Calculation of the contaminant removal effectiveness showed that the contaminant removal effectiveness can be improved compared to steady ventilation. Then the overall mean velocity level, you can see already that under time periodic ventilation, the velocity level increases, which basically is undesired if you would look at thermal comfort. Therefore, I did some further analysis. So in the monitoring points and at chest level and at ankle level, I obtained the maximum velocity, and I compared them to the acceptable condition mentioned by Ashray. For seated passengers and crew, these velocity levels should be lower than 0.36 meters per second, which is fulfilled. For more draft-sensitive body parts like the ankles, it's recommended to keep the velocity levels below 0.2 meters per second, which is fulfilled except for the symmetric supply, as you can see over here. So in short, time periodic ventilation can improve the ventilation efficiency without changing the supply flow rate, which shows the potential for energy savings. So we could reduce the supply flow rates without losing on the indoor air quality. However, the assumptions still require a lot of future work. More information can be found in this paper. This brings me to the conclusions of my presentation. So in part one, I constructed a new experimental simplified cabin mockup in which isothermal opposing sealing and lateral jets could be studied. I observed a qualitative agreement between the flow field in the generic setup and the flow field in real airplane cabins. And I did some quantitative analysis So I obtained information on the velocity and turbulence levels of the overall flow field and of the underlying flow components. In part 2, I assessed the accuracy of both RANS and LES simulations. RANS with the K epsilon models showed strong deviations in the jet interaction zone and along the merge jet, whereas the SST-K omega model showed improved performance because of the oscillatory convergence, and LES shows the best performance. However, computational times are strongly increased. And in the last part, time periodic ventilation was assessed, and it showed an improved mixing ventilation efficiency. So the air change efficiency and the contaminant removal effectiveness were improved. This is basically because these time periodic flow patterns, they cause a more efficient delivery of fresh air throughout the cabin. They dilute the contaminant concentrations more. However, we still need to do future work. Then my last slide to conclude my presentation, the novelties. It's the generic reduced scale setup that was constructed, the analysis of enclosed opposing wall and free jet flows, not only the overall inspection of the overall flow field, but also the underlying flow components. LES has been used, so a scale resolving transient modeling approach, again, focused on the fundamental flow components, and time periodic ventilation was assessed as a novel mixing ventilation concept for airplane cabin mixing ventilation, and we described the ventilation efficiency. Thank you very much.
Dames en heren, voor hier verder te gaan met het tweede gedeelte van deze zitting, namelijk de eigenlijke verdediging, wil ik u de leden van de examencommissie voorstellen in de volgorde waarin ze zullen discussiëren met de doctorandes. We will start with Professor Nesreen Chadar from the American University of Beirut in Beirut, Lebanon, and continue with Professor Maarten van Ierschot from the Faculteit Industriële Ingenieurswetenschappen KU Leuven, departement Werktuigkunde. Then we move on with Professor Johan Meijers, departement Werktuigkunde, and Professor Dirk Salens from the department Burgerlijke Bouwkunde Civil Engineering. And then we will have the supervisors of this doctoral research, Dr. Twan van Hoof from the Technische University in Eindhoven, Nederland, Professor Gert-Jan van Heest from the Technische University Eindhoven in Nederland, and Professor Bert Blokken from the Department of Civil Engineering, KU Leuven. Professor Nesreen Chadar, would you mind to start the discussion, please?
Yeah. Okay. Good morning, everyone. Good morning, Joe. That was really very nice presentation of your work. Made it much easier to understand and see the. Can you hear me?
Yes, I can hear you.
All right. So I just want to say the presentation was great. This is great effort. I just have a few questions to clarify for me.
Yes.
If you go to slide 6, when you were considering, the mixed ventilation and the deficiencies in mixed ventilation, what it does, it had two separate zones in the same row, all right? And in these rows, you had one group with the recirculating flow and another group with recirculating flow with the dilution not sufficient, to make the air quality acceptable. If this is my understanding. But in that system, if you have an infection source in zone 1, in one of the zones, the possibility of this moving to the second zone might actually be lower than if you go, let's say, to slide 18, when you were showing the mixed jet now with the supply, or any of the slides that shows this effect. Yeah. So if you have an infection source in one zone on the right, it could very easily be entrained and get to the other zone. Am I right in this or not? What is your answer to this? And would that actually compromise the improved dilution of contaminants in either one?
Yes, indeed. So indeed, this is also a known deficiency of mixing ventilation. It's called cross-contamination, when contaminants actually cross the barrier of the merge set towards the other side. Basically, what is mentioned in the literature is that you would like to keep the contaminants within one row. That's what is mentioned. So you would like to reduce the longitudinal flow towards the rows behind you or in front of you. So this indeed is an issue. So then the question may be, in case, for example, we use time periodic ventilation, will this be sufficient? Because using time periodic ventilation may even improve or may even make it worse, like could even stimulate the cross-contamination. But in case time periodic ventilation reduces these concentrations more, then I wonder if this really is bad. Of course, you don't want it, but I think that with a main air distribution system, as for example, mixing ventilation, you cannot fully keep the contaminants within one row only. Therefore, you might have to go to personal ventilation units, but I don't know if this is realistic to be implemented in an airplane cabin.
But what I also noticed that when you use the time periodic ventilation with this system, it performed much better in terms of localizing the contaminants, yeah, if I'm not wrong. So in a sense, if you do more work on that, as you said, in the future, you might actually find better parameters for, the optimal parameters for best operation of this. But you mentioned something about when you said that in literature, you try to keep the contaminants within one row.
Yes.
And again, there is another catch, Yani, that here you're talking about the two-dimensional model. But what happens if you have any disturbance in the aisle with someone, let's say, walking from back to front or front to back, or when food is being distributed, that creates additional disturbance that may, in a sense, enhance the entrainment and forward moving of contaminants to front or back rows, that is in the axial direction. So do you think the mixed ventilation model, the old one, would offer more protection from that axial movement than if you have the jet interaction at the, the jet merging at the center of the eye? It is just another thing to consider. I just want to hear your physical explanation of this, given that what I see that you have solved here is an actual fundamental flow problem, and you offered more physics and explanation of what goes on instantaneously and at steady and in the mean flow. But I want to understand more, how does this transport or the flow or contaminants forward or backward through the aisle to different rows?
Yes, indeed. So as I've shown here, I prepared an extra slide. So what we see here basically is the mean shape of the expired air. And you can see that under steady ventilation, so let's have a look at the 3D image over here. This expiratory plume is rather large, while under time periodic ventilation, so the bottom two images, this expiratory plume is reduced in size. So we can indeed, as you mentioned, reduce the longitudinal transport towards the passengers in front. Indeed, with mixing ventilation, so what I tried to mention is that the mixing ventilation is designed so they aim for keeping the contaminants within one row. But in reality, many studies show that typically the contaminants can spread to even 2 rows, or sometimes even further away throughout the whole cabin. Because as you mentioned, in case a passenger is walking along the aisle, it can drag these contaminants along the full passenger length. So this is something that is unwanted. And I think that time periodic ventilation also can can help in this respect, because it literally forces the flow field into specific states. So you get a better control of the full flow field. So these instabilities created by a walking passenger, they could be overcome to some extent, I think, using time periodic ventilation.
Okay, maybe other members of the jury ask additional questions, and if I have anything, I will state it later. Thank you.
Thank you very much.
Thank you, Professor Sadar. Professor Nielsen.
Okay, so Jo-Hendrik, first of all, thank you for the very nice presentation. I really enjoyed it. On one of your slides, you mentioned that there was a study saying that you should avoid transient behavior of flows.
Instability.
But I was wondering, why not go to the laminar regime, for instance? What do you think about that?
Is it possible in an airplane cabin, you think?
No idea.
I think with in an airplane cabin, it's might not be realistic because of all the movements of the passengers. I think this will be a transitional or a turbulent flow, indeed. Yeah, yeah. It might be indeed that you, with personal ventilation, you could have some laminar flow behavior. So then every passenger has its own micro environment. That could be. But with the main ventilation system, I don't think it can be realized.
And why not go to the fully turbulent regime?
Probably it's fully turbulent inside the cabin. The supply jets, they are in the transitional regime, but the merge jet, it will for sure be turbulent.
Yeah, but if you also make the injection jets turbulent, would that help?
Yes, it might improve the mixing, but then you're also restricted to noise issues, because for the turbulent regime, you will need higher supply velocities. I know that it's not possible anymore to increase the width of these supply openings, so you should go to higher velocities, and this can give some noise issues, can also give some comfort issues, because you increase the velocities inside the cabin. So.
And then you did a very nice study about changing flow rate periodically, which of course using CFDs is quite easy, but how do you think you could implement this in reality?
Yeah, I asked an airplane manufacturer whether this would be easy to implement or not. And basically you can, in an airplane cabin, you can control every inlet, you can set the flow rate of every inlet separately. That's really not a problem. So its implementation shouldn't be an issue. It's mainly, as I addressed, that with this sine function, you have a specific amplitude, a specific period. And in my study, I took the maximum value of this amplitude, which basically means that the supply velocities, in my case, increased to 2 times the steady state velocity, which will be too much for in real applications. As mentioned, this will cause noise problems and so on. So there's need to be future done. You need to do future work to do more investigations.
What I also found very interesting is the large-scale instabilities between the 2 jet interaction. What do you think about maybe you could tune those because they give a natural oscillation to improve efficiency, or do you think no, we don't need to change the inlet nozzles or something to optimize this process?
Yeah, indeed. So you mean with the lateral jets, for example, where you have this deflecting oscillations? Yes, indeed. So I know that this deflecting behavior, it is not always present. It really depends on the supply velocities, on the inlet height. In more fundamental studies, they also showed that it depends on the separation distance of the jet. So I think this unstable, or this unstable, it's more like a controlled instability, more or less. Indeed improves the mixing efficiency. So I think it would be very useful to do additional studies based just to see what if we change the inlet parameters to see what happens with the oscillating frequencies. Yes.
And maybe a final thing, I have to admit, you scared me a lot because up till now I never took care of where I would sit in an airplane, so I never booked in advance. So where should I sit to be the most safe?
Yeah, indeed. It's a very relevant question, of course. Let me check. I have some additional slides. It's this one. So I took a closer look at the passenger zone. I looked at the volume average concentration levels for each passenger individually. And then you can see that using time periodic ventilation, the aisle and middle seat zones, or the middle seat zone, the concentrations are reduced most. So depending on the ventilation strategy, you affect a specific seat. Under steady ventilation, and this is what your question is about, under steady ventilation, I've noticed that the lowest concentration appears for the middle passenger, for the window passenger, while the highest concentration occurs in the middle of the row. So in the middle, you have the stagnation zone. Contaminants can build up. So this is this is also confirmed by other studies, by the way. And the window zone, there you have the lowest concentrations. Yes.
And in front, in the middle, or in the back of the plane, does that matter?
It will probably matter. What I think matters the most is the location of, for example, the infected passenger. If you're sitting close to the infected passenger or not, I think that's the most important.
Okay, so suppose somebody starts coughing, where should I go? How far should I be?
If no one is coughing.
Yeah, someone's coughing.
Yeah, there could be some differences. I need to do future work for this. But yeah, I know there is some longitudinal flow as well. So this already shows that there are some 3D effects. So it could be different from row to row, I think. Yeah.
Okay, thank you. I feel a little bit more safe.
Thank you, Professor Scott. Professor Meers, please continue the discussion. Can we see Professor?
Yes. 1 moment.
Okay, Jo-Hendrik, thank you. Very, very nice, clear presentation about your work. It's very well done.
Thank you.
Yeah, I also have a number of questions, and I would like to start with a question about the ventilation system in the airplane.
Yes.
So if you're sitting in an airplane, it has its own personal little screw that you can open or close, right? With some personal air. So how big is that air supply compared to, let's say, the air per passenger that is foreseen in the plane, from the general system, say?
Yes. So the main air distribution really provides the largest amount of air. These personal nozzles, they can be used mainly for to control your thermal environment. If in case you feel too hot, you can open them. They won't really improve your microenvironment regarding contaminant concentrations, for example. But the main air distribution really provides the main amount of fresh supply air. Yes.
So what is the ratio of the mass flows per passenger, so to speak, that come from the main and that personal one?
This I don't know by heart. No, I need to look it up. I don't know. This is because I mainly focus on the main ventilation system. I didn't consider these personal nozzles in my simulations or in my experiments. So I need to look this up. Yeah.
And so because they are like, I mean, obviously their position is a bit random. Some passengers will open them, some will close them. What do you think that their impact is on the recirculation zones and all these kind of features that you see in your text?
Yes, I think that the main air distribution system really has because it has a high momentum, it will really control the overall flow behavior, and these personal jets will contribute, but it will not change, I think, the main flow behavior. I'm aware of a study, but this may not be related to this may not be an answer to your question, but I know a study in which they tested what happens if several combinations of nozzles are open and are closed. But this study mainly referred to what happens with contaminant concentrations, whether you should open or close it. It's not really related to the flow behavior. So I expect it to have a minimum effect on the overall flow behavior.
Yeah, I must say, if I'm sitting in an airplane, I never feel any general draft. I can choose to open that little wheel or not, and if I open it fully, then there is really some draft, right? It's kind of really, you feel it in your face or wherever it's pointed. But the general draft I never feel. So is that not an indication that at least locally there is some significant momentum, etc. in that jet?
Yeah, locally it can indeed be. Yeah, that in your personal environment, of course, if you open the jet, it's very close to your face. You will definitely feel it, and it might locally have a large impact. But I was talking more about that I don't expect it to affect the overall flow behavior. I think you will still have these large recirculation cells, for example.
Okay. Now, obviously, you've been talking about the difference between displacement ventilation. Yes. And so if you think about displacement ventilation, is that something that would be feasible using like personalized jets that are, let's say, coming from at the top of, from the top, and then essentially the exhaust is at the floor, so is that feasible, or are there reasons why that cannot be done?
I prepared a slide to show you some implementations of displacement ventilation. If all goes well, it should be projected now. So basically what you see here at the lower row, you can see some different kind of implementations of displacement ventilation. However, I should mention that these are all research studies. So they have been investigated also in realistic cabin mock-ups, but as far as I know, displacement ventilation is not being used in airplane cabins at this moment. It's mainly the mixing ventilation system. So what we see here, for example, in the second image, you can see that air is tested to come from below the seats, for example, or even from the ceiling with a low velocity. It flows down, will heat up at the floor, and then raise again. So different kind of displacement ventilation concepts have already been tested. I know that an airplane manufacturer already did some research on how to implement displacement ventilation, and these were studies from 2012. So they mentioned that they will see what happens with such research. So I have the feeling that it's not on point yet.
Okay. Given the examples you show, there is no example that really uses this overhead ventilation system, or is there the philosophy that every passenger should also have its own controllable little ventilation device?
What do you mean? That these examples I showed, that they don't include personal ventilation nozzles? Or?
Exactly, right. So as far as I can see, at least.
Yes, these indeed. Yeah. So most of the studies, they don't consider these nozzles open. I know there are some studies which are more fundamental studies which focus, for example, on the interaction point between the nozzle, between the main air distribution system and the thermal plume. But if you look at airplane cabin ventilation studies in general, in most cases, these nozzles are not considered indeed.
Okay. Okay, maybe so in your work, you provided obviously a thorough validation of RANs and LES versus experiments. And one of the, say, results, and I think you have similar ones in other tables, but one of the results is you can find in table 4.3. I think it's on page 126. So that's basically, you give this FAC2, RMSE for different predictions of velocity and Reynolds stress, etc. But I was wondering now, what does this mean? What can you do with this if you talk to a manufacturer?
You mean?
So in what way can you explain to a manufacturer that you can or cannot do something given this table?
And which table exactly? Which page? Because I cannot find it.
4.3, page 126.
126. Yes, indeed. So basically, these measures they compare they do either a point-wise comparison, like every data point obtained in the simulations is compared with the corresponding data point obtained in the measurements, or they could also first calculate the mean the mean variable and then do a comparison of the mean variables. So basically, what they say is that it shows which ventilation method, which stimulation method is better. It gives a general idea about the flow field. It doesn't give any detailed information on at which flow components one simulation performs better than the other. So, for example, if you would like to if you're interested in the mean velocity values, then you could look at these values just to check which of these validation metrics has the best performance for the velocity prediction, for example.
The question is, given your results, I guess what is driving manufacturers and in what way is your work helping them?
Okay.
So, for instance, what is driving the design of a manufacturer? What does he need to prove? I mean, typically, airplane companies don't make any, advertisement about the air quality, right? The price is what everybody is looking at typically, and not the air quality or not even the quality of the food, actually. So I presume that constructors are not driven necessarily from a commercial perspective towards increasing air quality, right? I think if you want to reduce price, actually, you probably want to reduce the air quality because it saves you energy. So how is this? What is driving manufacturers? How do they need to prove? What is the minimum that they need to achieve? And how can your work contribute to that?
Yes, indeed. Airplane manufacturers, indeed. So the indoor air, it should be controlled. Is it of main focus? As you mentioned, there are some economic perspectives they also keep in mind, of course. I think in my research with using time periodic ventilation, if you could supply the fresh air more efficiently, you could reduce the supply flow rate. So, which means that less energy has to be used. So then it could be beneficial for airplane manufacturers to more specifically look into the optimization of mixing ventilation, for example.
Right, but what do the manufacturers need to prove in terms of their ventilation system? And is your time periodic flow rate system, does that going to fit in that framework?
Yes, indeed. So basically, they provide a total or flow rate of 9.4 liters per second per passenger, and this flow rate is based on the air quality. It's even raised a little bit because they assume locally some poorly ventilated areas can be present, but indeed. I have to look into more detail.
So are you saying that if the standard, because I presume there's an ASHRAE standard, right, about this or something similar? Are you saying that the standard just says 9.4 per passenger, and then basically that's it? Then essentially they just make sure that it's 9.4 per passenger, and then they don't care about the rest, I presume.
No, what I mean is that this 9.4 liters per second per passenger is based on, of course, on some studies on the indoor air quality. And it's mentioned that they've noticed that at some parts of the airplane cabin, locally some lower air quality can be present, which is why it's even raised a bit more, up to the value of 9.4 liters per second. So I think from this perspective, they do care about the indoor air quality. But of course, the economic point of view is also relevant. Yeah.
Yeah, but I presume, I mean, same with food industry, right? I mean, if somebody wants to produce cheap meat and you don't impose some regulations or standards, then they're going to produce cheap, very unhealthy meat, right? That you can die from even. So yeah, I just wondered how the standards, because I think that's the only thing that drives probably the manufacturer, how
Yes.
the standards are driving, and maybe also what you need to do if you want to impose a new type of ventilation regime, and what you need to show to be able to reduce, for instance, the mass flow rate.
Yes, indeed. So I think the most important thing is, besides the indoor air quality, you also look at draft levels. So the comfort level is very important, like the temperature levels that can be obtained in the cabin, the air velocities. So this is also being considered, of course. And once more, I think if they can improve the ventilation efficiency, they might gain. They might save energy and thus economic costs, because this is, for airplane manufacturers, this is very, very relevant nowadays to optimize the thermal comfort and in order to distinguish themselves from competition.
Yeah, and so do you know that whether manufacturers are allowed to use CFD tools to prove that they gain certain levels of quality? You have any idea?
Yeah, we had contact with a section of an airplane manufacturer which are doing CFD simulations on the air quality. So we had some conversations, and they showed their CFD results. So they're really working on indoor air quality as well. Yes.
Okay. Thank you very much for your answers, Mr. Chairman. I'm finished with my questions.
Thank you, Professor Meyers. Professor Salmons?
Thank you, Mr. Chairman. Jo-Hendrik, I think you gave a very nice presentation about the very nice work that you've done. Of course, my duty is to ask some questions, which I will do, and I will start with asking you about the part 1 and 2, in which you used fairly simple models with 2D approaches, nothing in the cabin. Very simple approach. Of course, we all know it wasn't that simple. And in the third part, you go to more three-dimensional cabin approach with also people in there with chairs and everything you want. So from the result of part 3, can you justify, or can you say, okay, perhaps the two-dimensional approach with the empty box, is it sufficient to look at what really happens in a cabin? Because one could say it's all very nice to look at those 2D approaches and those empty cabins, but what's the point? Isn't it only an academic exercise that you do? So can you give some thoughts about that?
Yes, indeed. So we started by creating, or I didn't mention it during my presentation, but the inlet openings, they are considered to be 2D. So if you would use such an inlet opening, it's in an open environment, it would produce a 2D wall jet. Now, indeed, we have a 3D environment, and as I've shown you, it could be that indeed three-dimensional effects are there. So in future work, I would definitely measure in other planes as well, just to see what happens over the length of the enclosure. About specific differences, I know that when you include objects like passengers or seats in a room, this will give higher turbulence levels, locally higher turbulence levels, for example. So in my opinion, we should do future research as well, in which we include some obstacles in the experimental setup, because it makes it closer to reality, indeed.
Yeah. I agree, but I think that the difference is valid, but I think indeed in chapter or part 3, you show that there are limitations to translate the results to the real design of the cabin.
Yes, indeed, true.
Then I was also wondering about the novels, which were already addressed by Professor Meyer. We're also wondering about the details of the cabin skin, because it's not at all straight. There are a lot of roughnesses, details. To what extent do they change the actual flow that you have? And can you even play with them to improve mixing?
Yes, indeed. So you have many details along the geometry. So these can have an effect. For example, there are some openings along the below the overhead stowage compartment. So where you put your luggage in, there is a small opening, a slit. This could even affect the flow behavior. For example, it determines whether the jet remains attached to the overhead stowage compartment or not. So that is why I really would like to do measurements in a more realistic setup. So experimental measurements to take into account all these different boundary conditions as well. Yes, which could have an influence.
Yeah. Thank you. Then I was wondering about the energy use in airplanes. So one of your conclusions, looking at time periodic flows, was that you could reduce the airflow rate to have a similar indoor air quality as with mixing ventilation. Also, looking at the displacement ventilation, you mentioned at one point in your presentation that this has an effect on the heating, that it's not so comfortable to heat. Then I was wondering, okay, if you lower the airflow rate, if you look at, for instance, that displacement ventilation and the thermal effects, isn't this a reason why buoyancy effects could become more interesting to look at? Because lowering the airflow rate will bring you more in a mixed convection situation, where you state that the forced convection is the dominant flow regime, but if you lower airflow rates, then that does not longer hold. Also, when you want to look to displacement ventilation, I think it might be interesting to start looking into buoyancy. First, do you agree? I hope yes, but nevertheless, the second question is, how would you make an experimental setup to look into this buoyancy effects? Because it's not that straightforward on such a small experimental setup that you use.
Indeed.
So, what are your thoughts on that? Suppose you would get a little bit of money to make such a setup. How would you approach it?
Indeed. So first of all, I didn't conclude that you could use lower supply flow rates, I assume, because the ventilation efficiency improves. So this should still be investigated, of course. But I think with that this is valid in case you use steady ventilation. Then you really have a constant supply velocity that will interact with this buoyancy. While in time periodic ventilation, the inlet velocities still periodically will be relatively high. So I think that, of course, the interaction will be larger when decreasing the supply flow rate, but still less than compared with steady ventilation, I think. Because I've seen several studies which, for steady ventilation at least, they show the interaction between thermal buoyancy and between the momentum supplied by the inlets. And there you can clearly see that when jet momentum decreases, buoyancy takes over and you get completely different flow behavior. While I think with time periodic ventilation, this can be, to some extent, be overcome.
Also the link show, so it's the same as...
No, indeed. So there's some assumptions. Indeed, these are assumptions, of course. And then the second part, how to construct an experimental setup, including thermal effects. In a reduced scale setup, this is difficult. We were thinking at the start of my PhD to include thermal effects, but then, of course, the question was like, how can we incorporate these? And we were thinking about using thermal resistance foils, but we were a bit afraid that the heat would quickly be affected by the large supply flow rates. The air changes per hour is quite large. So that's why we didn't include it yet. But if I would include heat effects, I would rather use upscaled room like in Eindhoven, at the University of Eindhoven, where I was a visiting researcher for a short time to do these measurements. They also have a larger full scale setup, air-filled. So I would use that one for thermal investigations. Yes.
Because indeed, in the small setup, you need very high temperatures.
Yeah, indeed. And then of course it's still the question if you can realize hydrodynamic similarity. Yeah. So indeed.
Okay, then final question. Suppose you become part of the design team of Airbus and you get an empty page of paper, and they ask you to redesign the entire system because now you focus on the existing system. But you say, okay, I don't want to change because it's too expensive and so on and so on. But given the fact that probably the fact that we want to reduce the energy use of climatization in airplanes, we want to think out of the blue and we want to redesign the airflow, the airplane cabin to improve indoor air quality, to improve thermal comfort, and perhaps we can do something about the acoustics as well in such a cabin. So, what kind of approaches do you think are valid and which are less interesting?
Yes, indeed. So I think that if in case of COVID, well, when you have disease transmission and you would really like to avoid such a disease transmission, you should go to microenvironments so that every passenger or every row has its own controlled environment. I would go more towards such an approach. However, we should also take into account the cabin pressurization, so enough air should still be supplied to the cabin to pressurize it. And this will become indeed a very relevant question in the future when, because they are thinking to reshape the airplane geometry towards more blended wings, V-shaped airplanes. So then you don't have this single aisle airplane cabin with passengers sitting on each side of the aisle. So then indeed the ventilation system should be redesigned. And what you see in at least the nice drawings they show of the interior, you get like separate seating spaces with small tables, which actually it seems like they would like to increase social interaction. But maybe in such a situation, it might be easier to have like a controlled microenvironment for these separate spaces.
Do you have an idea how you would achieve this?
That's indeed a good question.
Are we then talking about local displacement ventilation, or what are you thinking about?
I think mixing ventilation is robust. From my conversations with the airplane manufacturer, they really they want to keep using mixing ventilation because of its robust design. So then you should, if you would like to change mixing ventilation, you should come up with a new ventilation system that's easy to implement, that's also is robust, which means that, for example, if you change the equipment inside the airplane cabin, you don't want the velocity field to change drastically. So that is what I mean with a robust ventilation system. So these are points of attention that we should think of when designing such a new ventilation system, I think.
But still, it's not very concrete.
No, so I think mixing ventilation is the way to go. In what kind of format? If this is via opposing jet flows, I don't know. These are some first thoughts I have.
Okay. Thank you for your answers. Thank you, Mr. Chairman.
Thank you, Professor Salmons. Dr. Van Hoof.
Thank you, Mr. Chairman. First of all, Jo-Hendrik, my compliments for the very clear and comprehensive presentation, as always. Of course, we had a lot of discussion already over the years, but I saved some questions today as well. My first question has a bit to do with the ventilation system that Professor Salmons also just mentioned. In your thesis, you studied mixing ventilation mainly. You mentioned displacement ventilation and the possible issues with stratification and draft and things like that. And then you also mentioned personalized ventilation systems, or personal ventilation systems. Do you have any ideas about how such a design could be done, where to supply air or exhaust air? Do you see this as a really feasible option, or is it more, well, let's check, but probably it will not work in practice? Can you elaborate a bit on that?
Yes. Such personal ventilation is already included in airplane cabins, of course, as you know, because of these nozzles you can.
Let's exclude the gas indeed. No.
Yeah, indeed.
You don't have those.
Yeah, indeed. So what I've seen in the literature is that they indeed come up with controlled microenvironments with supplies, nozzles integrated in the seat in front, for example, with also the exhaust is located in the seats, or another design is where the extraction of air is at the back of your seat. So in case you cough, it will immediately be extracted. But I don't see this implemented yet in airplane cabins. And these papers also mainly address that it will probably cost a lot of money to implement it. So I think this might be the main issue. Even if locally you can obtain improved air quality, these costs prevent them from being incorporated, I think.
Yeah, so financial aspects outweigh probably.
Yeah, I think. Yeah.
Thank you. Another question is more about the methods you used. You used PhD for the experiments, and you used the setup, and then you used RANS and LES for the CFD simulations. And after part 2, you concluded that LES is most accurate based on comparison with philosophies, manual stresses, film intensity, etc., etc. Of course, I agree. You show that it's better, more accurate, but it comes also with an increase in computational cost, quite a severe increase, you could say. So I was wondering if you look at for research, you want to have it as accurate as possible, probably, and also you want to have everything accurately predicted. If you would make recommendations to, for example, Airbus or Boeing or any other manufacturer about which methods to use for their optimization of the ventilation design, what would be your recommendation? Yeah,
obviously LES is not feasible to do a full design study, for example, or sensitivity study, where you have to do or have to perform many simulations. Then LES really takes way too long. So it's limited to academic research indeed. But as I've shown you, RANS simulations, they predict the overall flow components. There might be some deviations in the merge jet and the interaction zone, but the overall mean flow behavior is present. So what I've seen in such design studies that they basically use RANS with RNG K-epsilon model and go towards the adjoint method, in which they use to optimize specific variables like the inlet velocities, the inlet height. They use fast fluid dynamics. There are several options that can be used for faster simulations than LES. So, but for design studies and for industrial purposes, I wouldn't use LES. No, that's infeasible, I think. Now.
And does this choice or recommendation also depend on what you want to optimize that? Is it local velocities for draft issues, or is it like the more integral things like the air change effectiveness or the contaminant removal effectiveness? Does that play a role as well?
I think so, yeah. The reason why I investigated LES is because I really wanted to have a detailed investigation on all these turbulence stresses, because they contribute a lot, or can contribute a lot to the mixing. That was the starting point to use LES. Is it needed in industry? I don't know. I don't think so, because as mentioned, the overall flow behavior is relatively well simulated using RANS, for example. So,
thank you. One last very practical question. I noticed recently when I was flying once, again after years of not flying, and when having mechanical issues when taxiing already, so we were basically halfway the runway and we stopped. But then the ventilation system shut down as well. So you will try to optimize the ventilation system, but isn't the biggest gain that one could get if you would also start ventilating already when you're standing still somewhere with hundreds of people in one really enclosed environment? Do you know why they do it, and if there are directions to change that?
I know there are some guidelines that I think it was after a certain amount of time when the airplane is on ground. I believe it's 30 minutes. Then it's required to turn on the ventilation system, as I know. But why exactly they leave it out during startup phase? Sometimes I don't know. No.
Okay, thank you very much for answering my questions. Thank you.
Thank you, Dr. Van Moof. Professor Gerrit-Jan van Heijst.
Can you include them?
I hope you can hear me.
Yeah.
Yes.
We can.
Well, thank you, Mr. Chairman. Dear candidate, dear Jo-Hendrik, it's my pleasure to ask you some questions. And although we have been able to discuss a few items during the last few years already, it's a nice opportunity to ask you a few things about what you presented in your thesis and also in your presentation. I must say the presentation gave a very nice overview of what you have discussed in your thesis. Nevertheless, there are a few questions, and I would like to ask you some. First, about what you describe in chapter 3. It's about the PIV measurements that you did for the flow in the cabin. You have clearly indicated that the colliding sealing jets lead to a merged jet, and that shows a very remarkable swaying. So it's not let's say a flow that's stable or that's stationary. There is a lot of time variation in it. And also the lateral jets, they show time variance in the sense that they show deflecting oscillations. So different from the swaying jet in the case of the merged sealing jets. And I was wondering if you would choose between these two way of driving the flow in the cabin, which would be the most effective in terms of mixing?
Then, yeah, indeed. So what I notice from literature is that the lateral jet configuration has been studied a lot, and I think this is also the opposing jet configuration I would choose, because there you really have an interaction between these opposing jets, whereas in the sealing jet configuration, it might be, the mixing might be more limited, I think.
Yes, I think I fully agree with that. You can see that in the case of the lateral jets, they lead to this big deflecting oscillations, and that's really affecting the flow in these two main cells significantly, much more than the merged jet of the sealing jets would do. In the same chapter, you use an algorithm for vortex identification in order to track the vortices, and you use that quantity gamma. And for that purpose, you just choose a point P, and then you do the calculation according to that that formula that you give in chapter 3. I was just wondering, is this an automatic procedure, or do you have to choose the let's say the centers of the vortices by hand? Can you comment on that?
No, this is fully automized indeed. So for every data point, it will consider the surrounding data points, do the calculations, calculate the gamma function, and in this way the full flow field is automatically traced. So it's a very easy to use method, actually. Yes.
But you need to use all the let's say the points in the flow field in order to check what is the possible candidate for a vortex.
You can use it indeed. You can restrict these the investigation window to a specific area of the flow field. So you can choose the amount of points also that is surrounding the specific point at which you would like to calculate the gamma value. So there is a lot of tuning you can do. Yes.
I see. Yeah. I was just wondering, well, in the chapter where you introduced the time varying forcing, so the time change in the fluxes, you have just taken a period of oscillation. But how could you, let's say, optimize the ventilation or the mixing by just changing the period of the oscillation of the fluxes? I guess that would be a first guess, that it would be possible to find an optimum value for that. But how would you find it? What kind of criteria would you use in order to define, let's say, the best choice for the period of the time variance?
Yes, indeed. So the period I used was taken equal as one flow-through time. It was basically based on some preliminary CFD simulations. The CFD simulations did not incorporate opposing jets. It was with only one jet. And then I could indeed see that the contaminant removal effectiveness, the air change efficiency, reached an optimum for a specific period, which was equal to the flow-through time. So that's why I used as a first choice the flow-through time in my airplane cabin ventilation.
Yes, and the flow-through time, that's of course, I think, connected with the turnover time in the big circulation cells. Is that right?
Sorry, what did I didn't hear you.
So I think the flow-through time that you just mentioned would be related to the recirculation time in each of the two big cells. Is that correct?
Indeed, that's how I determined the flow-through time. Yes, it's really the time that pressure needs to cross the half of the cabin, actually, since I used two opposing jets. That's indeed the recirculation time. Yes, and to optimize this period, I would go to, as I explained, to Twan. I would do some design study indeed, where you can select several design objectives. For example, you could, for airplane ventilation, you would like to minimize the predicted mean vote. So the comfort, you would optimize, you try to optimize it. You could also implement an optimization of the air change efficiency and all these kinds of parameters. And then you can do this optimization calculations to find out which period might be the best, considering all these inputs, all these different inputs. And likely there will be a trade-off between these inputs. So you won't be able, I think, to optimize all of them. So it will be a trade-off indeed. But future work can focus on the optimization of the periods and of the amplitude of the inlet signal. Yes.
I see. Yes, clear. Then I have the last question. It was already mentioned that there is a potential effect, a 3D effect of, let's say, actual dependence of the flow in the cabin. So you have considered the flow in a cross section. Of course, that's the first thing you should do. But you can wonder what's happening in the actual direction. So in the longitudinal direction, as you mentioned it, in the cabin. Can you elaborate on that? What kind of effects would you expect to see? I'm thinking of the swaying of the jet, for example, of the merged sealing jets. The swaying, would it be uniform in the actual direction, or can you say anything about that?
Yes, I know from literature that longitudinal effects are present, which ideally you don't want, of course. You would like to keep the airflow uniform across the length of the cabin. But in reality, some longitudinal flow indeed exists. So if you would look at velocity profiles along the horizontal cross-section, you will see some variation indeed. Yes.
And do you think that's an important effect or not?
It is indeed, it can be an important effect if you would look at disease transmission, for example, that diseases, the bacteria, viruses, they are not contained within one row, and they can travel several rows indeed, yes.
Okay, well, thank you for answering. Thank you, Mr. Chairman.
Thank you, Professor Van Heijst. Professor Brokken.
Thank you, Mr. Chairman. Jo-Hendrik, thanks very much also for the very clear and comprehensive presentation. I have two short questions. One is about the comparison between the stationary supply and the instationary supply. You made it such that now over a certain period of time, the flow rate, the total flow, the average flow rate will be the same. But what do you think in terms of energy? And that actually, I think, boils down or connects to the questions also asked by Professor Salas and Professor Lewis. Could you say something about that? The total energy consumption if we would switch to this time varying approach?
Indeed. So there are several parameters affecting the energy use. For example, the amount of air that is supplied, the temperature. The supply temperature is important because the bleed air is extracted from the engine, so it's still at approximately 200 degrees when it reaches the air conditioning system. So if you could supply air at higher temperatures, then you should cool it less, so you could save energy. So this is what we need to investigate further. We've shown that because of the mixing ventilation efficiency improves, lower supply flow rates may have to can be used perhaps. So then we should add use less air, so less air should be cooled as well. So this could save energy. Regarding the temperatures, we should do future research with thermal conditions. Something that we should also keep in mind is because of these fluctuating inlet velocity, if you would calculate the kinetic energy at the inlet, which is calculated as the square of the velocity, which is higher. So this could indicate that larger or more energy has to be used for the driving fans of the ventilation system. So all these parameters together will result in the eventual energy use, and we need to do future research to really look at the effect of time periodic ventilation on energy savings. Yes.
And then one final small question. It's based actually on a photograph that I received from a colleague, and a colleague in Hong Kong. He also is working in airplane cabin ventilation and respiratory dynamics. And when he goes traveling by airplane, he has a nose mask with a plastic tube that is connected to a gas gun. Okay. That's how he takes care of his personal ventilation. What do you think about that?
I think this is a very safe way to travel indeed. But would it really be necessary? Like disease transmission, it depends on so many factors. It depends on the induced airflow patterns. It depends on the amount of particles that are released, how they are released. Is it by just breathing? Is it by sneezing? Is it by coughing? Are there walking passengers and so on? So it's a very complex problem. So to say that this is the way to travel, I don't know. So is it dangerous to travel without such without such a mouth mask? I think it's relatively safe to travel in an airplane cabin, given the high supply flow rates, for example. But it's difficult to say indeed. Yeah.
Okay.
Yeah.
Thank you very much. Thank you, Mr. Chairman.
Thank you, Professor Brocken. Does this suffice for the medical examination board? No more questions? We'll check whether there are questions in the chat.
Yeah, there were no questions here.
No questions. Dames en heren, dit is een publieke verdediging. Dit is de public defense. Dat betekent dat u ook de kans hebt om een vraag te stellen of een opmerking te maken. You also have the right to ask a question or to make a comment. Are there any comments or questions from the audience? Zijn er vragen of opmerkingen uit het publiek? Zo niet, dan zal de jury zich terugtrekken voor de vraagstelling. To the members of the examination board who are online, they have to switch to the other link for the deliberation. See you there. Dames en heren, geachte collega's. Ik geef u kennis van de uitslag van de beraadslaging van de examencommissie, aangesteld voor de graad van dokter in de ingenieurswetenschap. De heer Jo-Hendrik Thysen heeft aan de faculteit een proefschrift voorgelegd, handelend over experimentele en numerieke analyse van isotherme tegenoverstaande stralen ter verbetering van de mengventilatie-efficiëntie in een vliegtuigcabine. Experimental and numerical analysis of isothermal opposing jet flows towards improving airplane cabin mixing ventilation efficiency. Dit wordt verkrijgen van de graad van dokter in de ingenieurswetenschap. Hij heeft het proefschrift in openbare zitting voor de examencommissie verdeeld. De examencommissie heeft vastgesteld dat zowel aan de wettelijke en decretale bepalingen als aan de voorschriften van het universiteitsreglement werd voldaan. Na beraadslaging verklaart de examencommissie dat de heer Jo-Hendrik Thysen voldaan heeft aan alle eisen voor de proef en de graad van dokter in de ingenieurswetenschappen behaald. Bijgevolg. En in naam van de rector van de KU Leuven verleen ik u de graad van dokter in de ingenieurswetenschappen richting bouwkunde. Proficiat, dokter Thysen. De zitting is gesloten. Het is de gewoonte dat een van de promotoren een relatie houdt met de blokken en dan moet
Beste Jo-Hendrik, dear Jo-Hendrik, hier sta je dan, zit erop. Ik heb voor jou een Latijnse quote gekozen. So I chose a Latin quote for Jo-Hendrik that says: "Perfer et ordura dolo hic tibi podent." Small letters. And that means be patient and tough. Someday this pain will be useful to you. And it refers to the PhD process, which is not always joy. There are highs, there are lows. I will talk about that a little bit later. In 2015, you graduated from Eindhoven University of Technology as a Master of Science in Applied Physics, specialized in transport physics. And you did that in the group of Professor Gert-Jan van Heest, who is one of the promoters today. And before your graduation already, you indicated that you would like to embark on PhD studies and that you actually would prefer to do that here at this university. At that time, of course, you already knew about the very high grades you received in your bachelor studies in Hasselt, but also in your master studies in Eindhoven. And actually later, with your master thesis, you obtained the IBIPSA Netherlands Flanders Best Thesis Award. That was also in 2015. So it was clear that you would be an excellent candidate to embark on PhD studies. Of course, when you want to have a new PhD student starting, you also need funding. And we weren't successful from the very beginning. So in the first year, here at our department in this university, you worked as a researcher and you did several projects. Many external projects on pedestrian wind comfort, pedestrian safety, cooling capacity of ceiling panels, a bit also airplane cabin ventilation already. That was the precursor to the actual study. And you worked on preparing your PhD proposal. And that was submitted to FWO Flanders, research fund in Flanders. And it was highly valued there, so you got funding and you could start on this study. So this study was actually, as you have seen, partly numerical, partly experimental study. And for the experimental part, Jo-Hendrik spent quite a while at the laboratory of Professor Gert-Jan van Heest, working with the PIV setup there and actually constructing the experimental setup at the water-filled room that you have seen. So actually, in detail, you started your PhD officially, I think, if I don't remember, it was January 2017, and the rest is history. And I will not talk further about the
details of the research itself, well, you've seen that here, and apparently he has also written a book about it. It's quite interesting, so for the holidays I can warmly recommend to take that to the beach with you. But maybe a bit more on the personal side. I think that today is a special day for you, a special day for your parents, your family, your friends. It's a new milestone in your life. I think one that you will certainly also remember, because it's taken a long and hard road and hard piece of work to get here. But it's also a special day for your supervisors. Every day, and it doesn't happen too often, but every day that a PhD student graduates, and certainly with an excellent thesis like this, is also for us a very pleasant and enjoyable day. So this marks the end of a journey, Jo-Hendrik, that you have lived here together with us, together with your colleagues, and that sometimes, unavoidably, also has been an internal struggle. And maybe that's a bit difficult to understand for people that have not been involved in PhD studies, but it's not always fun. And there's also quite some stress sometimes in the PhD study, components that are not delivered, computer simulations that are crashing, setups that start leaking, laboratories that get flooded with test water and so on. And indeed, if a PhD study would always be easy and enjoyable and entertaining, everybody would do it. And that's not the case. And then it also would not have the value it actually has. So no pain, no gain. I think that certainly applies. And yeah, especially I think in the last year, the amount of work qualitatively and quantitatively that you did is really amazing. So you've done indeed excellent research work, where I think almost every chapter has been published or is in preparation for publication in a high-quality scientific journal. And I think that I speak also on behalf of the other two supervisors that we're also very proud of you and very proud of your research work. It's also known in Belgium that certainly this time of year, that is increasingly known that we have a lot of good sprinters. And Jo-Hendrik is also a good sprinter. If you indeed see how he actually has speeded up his work towards the last year, where actually all the chapters and the papers have been written in the last year, yeah, that is quite amazing. So I have no doubt also that your family is also very proud of you, and I really want to thank them for the trust they have placed in our department and in our university. I also would like to thank very much Dr. Twan van Hoof and Professor Gert-Jan van Heest for having joined the supervisory team. And of course, I also would like to thank the members of the committee for their work and for their dedication also to this procedure. So Jo-Hendrik, this has been a rather long speech, and it's almost lunchtime, I think, so I'll not make it too much longer. And I can say still many things about you here, but I'll keep it brief. 5 final comments. First one is that yeah, you did really a great piece of work, and I know for sure that there is someone burning with impatience to read this thesis, and that's our friend Andreas Wiek of Airbus. So I'll have to send it to him, and he will enjoy that in the summer holidays. So it's also a piece of work that you did in your typical, very meticulous way, and that is very highly admired and appreciated. Second, we, and that is me and all other members of the team, are very proud that you have been one of ours. You will always be at home here in our department, our university. We thank you for having been part of our team, and we wish you the very best for an undoubtedly great and very successful future.
First of all, thank you for coming. I really appreciate all the support. It's really of high value to me to see so many faces. Also, I know that a lot of people are watching online, so I think without all of you, it wouldn't even be possible to do this PhD journey. And first of all, I would like to thank the members of my examination committee for their time to assess my thesis, for all the questions. I really think the thesis has been improved. So I also learned a lot from these questions. I have a very small gift for you. So I hope you like chocolate. Then I would like to thank my supervisor, Bert. Thank you for all the years. Thank you for allowing me to do a PhD here at KU Leuven, and really an amazing research group with a very high level of knowledge. So I really learned a lot. I learned a lot from your expertise as well. Thank you for sharing all your knowledge on CFD, PIV, all your knowledge on writing papers. I really appreciate it. So I have some more gifts for you. Each time we went for a drink, I think that you drink some gin tonic, so I hope you'll like it. Thanks. Then I would like to thank my second supervisor, Professor Van Heest. Gert-Jan, I've met you as a student in one of your classes, and it's because of you that I got really interested in fluid flows. So you were also my promoter for my master thesis. And after my master thesis, as Bert already mentioned, I wanted to do a PhD at KU Leuven. But therefore I asked you, I still remember it, Professor Van Heest, do you know a Belgian professor? And it turned out indeed that you had, knew Professor Blokke at KU Leuven. So this was also a university where I wanted to do a PhD. You introduced me to Twan, and this resulted in this PhD work. So I'm very happy that you gave me this opportunity as well. Then Twan, as my co-supervisor or daily supervisor even, we had a lot of meetings. I really enjoyed these meetings. It was not always about research. I really enjoyed just the normal chats. I enjoyed going with you together to conferences. So you learned me a lot. We had a lot of discussions. You proposed many new ideas, sometimes way too many. I couldn't implement all of it. So, but really, it's really appreciated. So also for you, I have one.
I'm curious what that will be.
Okay. This is a good bottle of wine.
Ah, perfect.
I hope you like wine.
Yeah. Next one.
Okay. Then I would like to thank the professors of our section, Dirk, Hans, Staff, and Bert, for creating such a great atmosphere at work. You really select the good PhD students because we connect all very well. I really enjoyed working because I think if the atmosphere wasn't that great, I wouldn't be working from the early morning till the early evening. I really would like to thank all my colleagues, but to some of you, I would like to say a few words more. First of all, Fabio, you couldn't be here, but I know you're watching. You really helped me a lot with all the CFD simulations, and I already mentioned it to you really a lot of times, but you always say, no, it's not a problem, so you remain very modest, but still you really helped me a lot, also with all the explanations on how to prepare the preliminary defense, how to prepare the public defense. So a very big thank you to you. Then I would like to say to Tianfeng, Astrid, Evie, Ina, Juliana, which are PhD students that more or less started at the same time as me. We had a lot of nice conversations, and we were always dreaming about life after PhD, how nice this could be. And now I can finally say that I made it. So also special thanks to Katja, Ayash, Tuhit. You guys, every time you were doing some activity after work, you came to my office to ask, like, would you join us? Even if you already knew beforehand that the answer would be, no, I can't, I have to work. But every day you came to my office asking if I would join. So I really appreciate it. Then I would like to Also thank Jason, Abdella, Patricia, Krista for all the arrangements that they did during the past years, past months, for sure. Now I would like to switch to Dutch because I think saying thank you in English is actually quite difficult. Probably you hear the word thank you quite a lot of times now, so it's easier to continue in Dutch. Dus eerst en vooral wil ik ook Daan bedanken. Jij werd een student bij mij, bouwfysica, zo heb ik je leren kennen. Dan ben je mijn collega geworden, nu zit je zelfs in hetzelfde kantoor als mij. En ik moet zeggen, om het op het Limburgs te zeggen, ik heb me echt al kapot gelachen met u. Ik heb me kapot geamuseerd. Ik vond het echt heel fijn samenwerken met u. Vaak samen avondeten, veel praten. Dus ik ben heel blij dat ik u heb leren kennen en dat je mijn collega bent. Dan nog mensen buiten het werk die ik heel graag wil bedanken. Vanaf het eerste jaar doctoraat ben ik bij de basketbalploeg KU Leuven terechtgekomen. En dat waren echt voor mij, dat was een topteam voor zowel de mannen als de vrouwen. We vormden zo'n echt team samen, ook buiten het basketbalveld. En ja, ik heb heel veel goede herinneringen aan alle culturele uitstapjes naar de Oude Markt. Dat ga ik ongetwijfeld nooit vergeten en ik hoop dat we dat nog eens kunnen overdoen. Dus jullie hebben sowieso een speciaal plaats in mijn hart. Dan de boys van Basket Stevoort ook aanwezig. Sommigen zijn live aan het kijken. Basketbal, zeker de laatste maanden of het laatste jaar, dat was voor mij echt een ontspanning. Het ging niet alleen over competitie, het ging ook over plezier hebben, samen op vakantie gaan, een hechte groep vormen, na de match samen nog in de kleedkamer blijven. Dat was voor mij onvergetelijk en nodig ook om alle stress van het werk te kunnen vergeten. Dus ik kan jullie daarvoor niet genoeg bedanken. Dan Jeugdhuis het Geverke, ook heel goede vrienden van mij. Sedert, ik weet niet hoe lang al, sinds we heel jong waren waarschijnlijk. Hè. Merci om hier aanwezig te zijn. De laatste maanden, jaren heb ik niet altijd kunnen bijdragen als er iets aan iemand zijn thuis gedaan moest worden, verbouwd of weet ik veel wat. Hè, want het was altijd nee, ik ga het niet, ik moet nu werken. En nu heb ik in één keer tijd te veel, dus als ik u kan helpen, je hoeft maar te bellen en ik sta daar. Ik kan altijd op jullie rekenen en dat is sowieso wederzijds. Dus een heel dikke merci. Dan ook dank u wel aan Marieke, Jan en Aniek voor alle steun en liefde die zij mij gegeven hebben de laatste jaren. Dat apprecieer ik enorm. En tot slot wil ik mijn familie bedanken. Dus eerst en vooral opa en oma. Jullie zitten thuis te kijken, jullie konden niet hier zijn. Maar ik neem sowieso een geprint boekje mee en ik heb het zelfs gehandtekend voor jullie. Dus ik denk wel dat jullie daar blij mee zijn. Dat heb ik toch van horen zeggen, al heel vaak. Mijn tantes, mijn onkels. Familie is heel belangrijk. Zeker een heel dikke dankjewel aan mijn meterke, tante Joke en onkel Marcel. Jullie staan altijd klaar voor mij. Maakt niet uit wat ik doe. Is het basketbalwedstrijd? Is het huisvesting zoeken hier? Doctoraat afleggen? Jullie zijn er altijd en dat valt met geen woorden te beschrijven hoeveel ik dat apprecieer. Dus dikke dankjewel. En tot slot, om af te ronden, mijn ouders, mijn zus. Ja, mijn mama kon niet hier zijn helaas, maar ik weet dat ze thuis heel enthousiast en meevolgen is. Merci voor alle steun. Ik weet dat jullie dat uit liefde doen. Ik apprecieer dat enorm. Jullie staan altijd voor mij klaar. Dat is sowieso wederzijds. En ja, ik hoop dat we snel nog eens in de lunchgarden kunnen gaan eten, ons favoriete restaurant. Dus bij deze. Dank u wel allemaal.